In this lecture, we will go over the CFA Level 2 reading on multiple regression and issues in regression analysis. This reading takes off where the previous reading left. In the previous reading, we just had one X, so we had one independent variable, and as this name implies, we will now have multiple independent variables. The fundamental concepts will be covered in section 2, and I'd say this is one of the most testable sections in quant. Then we talk about the concept of dummy variables, where the variable can take a value of 0 or 1. After that, we get into violations of regression assumptions. We saw some regression assumptions in the previous reading. Here we will see those assumptions again. And then we'll talk about certain assumptions that are violated often and how to deal with those violations. Then we'll talk about model specifications. This refers to how we define a model. We say that Y depends on X in this way. That is specifying a model. What is the concept behind specifying a model, and what are the typical errors? We are learning these typical errors so that we don't make them, or so that if somebody else has done a regression and we evaluate, we can tell whether they have made some classic errors or not. And then there is a small section at the end which deals with qualitative dependent variables. Let's start with section 2, which is the main one. Multiple linear regression allows us to determine the effect of more than one independent variable on a particular dependent variable. This looks a lot like what we saw earlier. The Y is our dependent variable. Here I have shown two independent variables. Could we have 3 or 4? We could. And then these are called regression coefficients or slope coefficients. That is referred to as the intercept coefficient. Before I go into a detailed example, I just want to give the simple concept over here. When you plug numbers into a computer, so you specify a model and then you give your regression model or your software, you give it the data. It will spit out a regression equation and give you lots of information. That is information that we are going to evaluate over the next hour or so. And then your job will be to analyze the information that is given to you and then figure out whether there are any violations, figure out that with a particular value of x1 and x2, and given these coefficients, what should the dependent value be. Sometimes we'll have a straight relationship where x might be a given number, x1 will be a given number, x2 a given number, and we predict y. But more often than not, you'll have to do transformations. And that is what we are going to see in this example. I'd say that this is the most important example in this reading, so make sure you understand it very well. As the manager of the trading desk at an investment management firm, you have noticed that the average bid-ask spread of different NASDAQ listed stocks vary widely. The good thing about this example is that it's very related to what we studied. So we are looking at the bid-ask spread, and I hope you know what that is. We've studied that at level 1. So you are noticing a disparity. There is a range in that bid-ask spread. When the ratio of a stock's bid-ask spread to its price is higher then for another stock, your firm's cost of trading in that stock tends to be higher. This is just setting up the business case. Okay, so you don't like the fact that the bid-ask spread is very high because that increases your cost. So you formulate a hypothesis that the stock's percentage bid-ask spread are related to two things. One is the number of market makers, and the second is the company's stock market capitalization. So there are several important points being made here. There is an underlying business, but this particular reading isn't about the business. However, knowing the business is helpful. Why do you think we are looking at bid-ask spread as a percentage of stock price? Because if you have a stock price of 250, then a bid-ask spread of 10 basis points is small. If the stock price is $1, then the bid-ask spread of 20 basis points will be huge. So it's the percentage that matters. Okay, so that's one point. Now to check your understanding, if you take this bid-ask spread, and when I say BAS, I'm referring to the percentage bid-ask spread, that's a given. We are saying that this is a function of the number of market makers. So these are the major dealers, you can call them the big brokers, the broker dealers. So do you think there is a positive relationship or a negative relationship? The more the market makers, the less the bid-ask spread. And the market capitalization, do you think the spread is more for large market cap companies or small market cap companies? It makes sense that the bid-ask spread is small for larger market cap companies, because larger market cap companies tend to be traded more often. Okay, you don't need to really know all this in the context of quant, but you need to know all this as a CFA level 2 candidate. All right, so you come up with a particular specification. You say that your dependent variable depends on these two things. So the bid-ask spread is the dependent variable. It depends on what two things? The number of market makers, and it depends on the market cap. Now, if you just think about this, do you think we'll have to do some transformations? Because market cap is in millions, billions of dollars. The number of market makers is 5, 6, 7, 8. So clearly just purely taking the actual numbers would not make any sense. We need to do some transformations. And one of the most common transformations we do is a natural log. So we take the natural log of numbers. And in case you are confused about what to do when, the hint is given in the excerpt over here. And I've actually taken an excerpt from the example. I've not reproduced the whole example. A log-log regression model. Log-log regression model is where you are taking the independent variables, such as market makers and market cap, and taking the log of that. And the dependent variable, you are also taking the log over there. That's called a log-log. A log-log regression model may be appropriate when one believes that the proportional changes in the dependent variable bear a constant relationship to the proportional changes in the independent variables. So when X% change in one has a certain percentage change in the other, percentage changes means generally that you should take a log-log. But by and large, in your CFA level 2 exam and practice questions, they will tell you what the transformation needs to be. And that's given right here. So it is specified. The Y is the natural log of the bid-ask spread percent. X1 is the natural log of the number of market makers. And X2 is the natural log of the market capitalization measured in millions of dollars. All right, so this is setting up the question. So we take the data and feed it to the regression software, and this is what the regression software spits out. I can almost guarantee that you will see something like this on your exam, because you are looking at a regression output and then you are looking at ANOVA, analysis of variation. You will have to interpret this. And I'm going to walk you through the most important aspects of this output. This is the intercept term, and then what do you think this term is? Minus 0.21. This is B1, the first coefficient, the coefficient associated with the market makers. And then this is B2. Given this, and without looking at anything else for now, can you write out the regression equation? That is going to be Y is equal to minus 0.75 minus 0.279 times x1, and then minus 0.663 times x2. And then there will be an error term. But what's the expected value of the error term? It is 0. So this is your regression equation. What is Y over here? It is the natural log of the bid-ask spread percent. What is X1? It is the natural log of the number of NASDAQ market makers. and x2 is the natural log of the company's market cap in millions. Does it surprise you that both the coefficients here are negative? Actually, it should not surprise you, because that's what you would expect. You would expect that if the market makers are more, there are more market makers, then the spread should be low, and you would expect that for larger market cap companies like Microsoft and Oracle and so on, the spread will be lower. Okay, so this is your equation, and that's the first thing that you should be able to do out of your regression output. Now, the next thing to do is to figure out whether these coefficients are statistically significant. Actually, before we go into the statistical significance, I want to give you another interpretation of these coefficients. One interpretation of the coefficients is that these are like elasticities. Why? Because if x2 goes up by 1%, what will happen to y, all else equal? It will come down by 0.66%. Similarly, if x1 goes up by 1%, then y will come down by minus 0.279%. So the curriculum says this several times, and you need to know this, that the coefficients can also be thought of as elasticities, all else equal. All right. Now the next point is evaluating whether this is really statistically significant. So you see it's a negative 0.27 and this is minus 0.66. To see whether something is statistically significant, whether there really is a relationship between x1 and y, we take a null hypothesis. That null hypothesis is that the coefficient is what? Is 0. There is another way of looking at it. You actually believe that B1 is negative, right? So that is your belief. So you set up the null as something that you would like to reject, right? Do you think this is a one-tailed test or a two-tailed test? This is actually a one-tailed test. If your belief is that B1 is negative, right, that means you are only on one side of the tail. So you need to set up a one-tailed test because you'll only be concerned about one side. The null hypothesis, and I'll just make a side remark over here, those of you who are weak with null hypothesis and this hypothesis testing in general, my level 1 video on hypothesis testing is free on the website. So if you go back and listen to that, it would be very helpful. That directly relates to what we are talking about here. So back to this. The null hypothesis is that B1 is greater than or equal to 0 versus the alternate hypothesis that B1 is less than 0. Okay. So how do we now test this hypothesis? We do the standard t-test. So we come up with the t-statistic, which is actually given. You can just look at this. -4 looks like a fairly negative number, so you can reject. But if you want to be more diligent, you can take this. You can say that at the 5% significance level, the critical value is whatever. And we've studied how to do this before. It's all available in the level 1 video. And then you will be able to reject. But what I want to see is, can you look at the relationship between the standard error and the t-stat? If you are only given the standard error, can you come up with the t-stat? This is also level 1 material. The t-stat is equal to the amount estimated. This is from your sample data, because effectively regression is based on sample data. So what was the formula for the t-stat, given that you are doing a t-test over here? That formula, and this is something we saw in the previous reading also, minus 0.279 minus the hypothesized value, which is 0, divided by the standard error, which is given. So that is 0.0673. When you do the math, you should come up with this number. And then standard hypothesis testing. You compare this with the critical value. So since this is a a one-tailed test. You will have, depending on the level of significance, you will have a critical value which is maybe -2 or -2.56 based on how much significance you want to work with. But clearly -4 is going to be way to the left. So do you reject the null hypothesis or do you not reject the null hypothesis? We can then reject the null hypothesis in favor of the fact that there does appear to be statistical significance. Then what about this next one? Relationship with market cap. This is -27. So this also looks very statistically significant. The curriculum goes through and does all the calculations, but clearly you can see without too much more work that both these coefficients seem to be statistically significant. All right, so what have we done so far? We have analyzed the top part of your regression output. Next, let's look at this part, the analysis of variation. I did the top part first just because we see it first, but if you were doing a real analysis, you first look at analysis of variation, because this is telling you at a high level whether the overall regression is significant or not. And to figure out whether the overall regression is significant, you look at the F-stat and then this significance. What I'll describe here is, at this stage I'll just talk about this at a high level, and then there are examples later where we get into this in more detail. But a high F-stat is a very good thing. This means you can reject the null hypothesis that all the coefficients are 0. A high F-stat means a very low p-value. The significance of F is the p-value. When you look at these numbers, this implies that you have reasonable statistical significance at an overall level. If your significance here had been a large number and the F-stat had been a small number, then you would go into a little more detail before evaluating these numbers. And just for completeness, if we look at the bottom part, this is the overall residual standard error, and then we have the multiple R squared, which tells us about explained variation as a percentage of total variation. Generally a number of 0.5 is considered reasonable. And then we also have the number of observations, which is 1819. The next step will be, and I can guarantee that this question will always show up, you will be given numbers for x1 and x2. So you will be given the independent variables, and you will need to use those independent variables to come up with the dependent variable. Before I solve this for you, I'm going to try and have you do this. So if I tell you the following, if I tell you that the number of market makers is 5, and I tell you that the market cap of a company that we are evaluating, so the market capitalization is 100 million. Remember, we are dealing in millions over here. So I have given you the x1 value and x2 value for a particular company. You have verified that this regression looks good. You have the coefficients. What is the bid-ask spread percentage that you would predict for this company given this regression model? So this is the regression equation. The output is equal to -0.76, and I'm rounding to 2 decimal places, and then -0.28, which is coming from here, times x1 -0.66 times x2. But here you need to recognize that we have done transformations. x1 is the natural log of 5. So what will that number be? If you take natural log of 5, which you should be able to do on your calculators, that should be 1.6. So you plug in 1.6 approximately. The curriculum has the exact numbers, but here you need to get the concept. What is x2 going to be? x2 is the natural log of 100, and when you do that, you should get approximately 4.6. So then you have y is equal to minus 0.76, minus 1.6, minus 4.6. What do you get? Approximately minus 4.26. Are you done? Not quite. Why? Because this is log. Okay, so the natural log of the bid ask spread percent is equal to minus 4.26. And if you remember your basic class 10 maths, natural log means that you have base e, and then e to the power of, so e to the power of this number minus 4.26 is equal to the bid ask spread percent. On your calculator you do e to the power of this and you should get 0.0141. So this is equal to 1.41%. So this is powerful. Given this regression and given a company's market cap and given the number of market makers, you can predict the bid ask spread percent. And you need to know how to do this because, as I keep saying, at least one question on your regression related analysis will be, here is x1, here is x2, here are the coefficients, calculate what the predicted value for y is. What you need to do now is read examples 2 and 3. They are based on similar concepts. They are simpler than what I've talked about, but they are all part of your practice. We now come to section 2.1, assumptions of the multiple linear regression model. This is a fairly straightforward section. You need to learn these assumptions and they should look familiar. To a large extent, you saw these assumptions in the previous reading. In order to make a valid inference from a multiple linear regression model, we need to make the following 6 assumptions. The first one, the relationship between the dependent variable y and the independent variables is linear. What if the relationship is not linear? Then you need to do transformations as we did with our example. Second, the independent variables are not random. Also, no exact linear relation exists between 2 or more of the independent variables. And this is fairly self-evident. Third one, the expected value of the error term conditioned on the independent variables is 0. In other words, you cannot predict the error term based on the value of the independent variables. Number 4, the variance of the error term is the same for all observations. You don't want a situation where as x is increasing, the variance is increasing. That is something called heteroscedasticity, which we will discuss later. Then 5, the error term is uncorrelated across observations. Just because you know an error term, you should not be able to predict the next error term. And finally, the error term is normally distributed. Obviously, it would be distributed around 0, and the distribution is normal. So you need to stare at this for a little bit and memorize these 6 assumptions, because I can easily see a question where you are tested on these assumptions. Which of the following is not an assumption of multiple linear regression? So there will be 3 that all sound good, of which 2 will be from this list. All right, now coming to section 2.2, and in a sense we've done this. We are talking here about predicting the dependent variable in a multiple regression model. To predict the value of a dependent variable, this is the y value, using a multiple linear regression model, we follow these 3 steps. So have we done this before? We've just done this. We obtained estimates of B0 hat, B1 hat. What does the hat mean? That these are estimates. They are the estimated values. And the regression parameters are B0, B1. So when we do the regression, we get the estimate of the parameter values. Where does this come from? The software, regression software gives this to us. and we just saw these numbers. Determine the assumed value of the independent variables. And how did we just do this? We said that the assumed value of x1 is that we have 5 market makers. Assumed value of x2 is that the market cap is 100 million. So we get those values. And then we compute the estimated value of y based on the values of the coefficients and the values of the independent variables. Why is there no e? Because the expected value of e is 0. So if you really want to practice this, do example 4, but since we've already done it, I'm not going to spend time on this lecture. Section 2.3 now, testing whether all population regression coefficients equal 0. To test the null hypothesis that all of the slope coefficients in the multiple regression are jointly equal to 0, and that is shown over here, h0, that b1 is equal to b2, etc., all equal to 0, against the alternative hypothesis that at least one slope coefficient is not equal to 0, we must use the f-test. And I hope you remember this from before. You do the f-test. If you do not reject the null hypothesis, what does that mean? That means you cannot reject the fact that all your coefficients are 0. If all your coefficients are 0, then the regression is not telling you anything. So the first thing that you do is you establish the fact that you can reject this null hypothesis. So you do the f-test. To do any test, you need the statistic. So you need the f-stat. And hopefully you remember this from the previous lecture. The f-stat is equal to the mean regression sum of squares. What's the mean regression sum of squares? You take the regression sum of squares and divide by k. What's k? K is the number of coefficients. What was k in the previous reading? It was 1, because you just had one independent variable. Now if you have 2 independent variables, then what will k be? 2. So if we go back to example 1, where we talked about 2 independent variables, the number of market makers and the market cap, what's k? It is 2. So the mean regression sum of squares is the RSS, which is this regression sum of squares, divided by 2, which will give you this number. What about the second thing, the mean square error? The mean square error is equal to the sum of square errors divided by, and you just need to remember this, I'm not going to derive this, n minus k plus 1. What is SSE? That's given over here. And then where is this number coming from? So it is SSE, which is this large number, which I will not rewrite. So SSE divided by n minus k plus 1. What is n? N is the total number of observations. That total number of observations was how much? If we go back to our data, it is 1819. So you actually do 1819 minus what's k? It's 2, the number of independent variables, plus 1. What is 1? That's just part of the formula, right? So then you have SSE divided by 1816. When you do that, you will get this number. All right, so then this is your MSS for the residual. It is called the MSE. These things look complicated, but I hope you remember it from the last lecture, and I say it enough times so you can then just try to memorize. And then how do you come up with the f-stat? It's the ratio of those two numbers. It's MSR over MSE. And those who are studying from other study notes, sometimes they use different symbols, so be careful. Obviously, on the exam, these are the symbols that will be used, so make sure you are on top of this. You come up with the f-stat. Does this look significant? It is very significant. And remember, a high test stat means a low p-value. This test stat is so high that the p-value is effectively 0. To 2 decimal places it is 0. Based on this, what can you say? You can say with a lot of confidence that at least one of the coefficients is not 0. So we can reject the null with a lot of confidence. That is the point over here. Next discussion, section 2.4, the adjusted R squared. And again, I'll connect with the previous lecture and then take you forward. What is R squared? It is the total variation minus unexplained variation, which is the explained variation divided by total variation. This formula came from the previous reading. When we have one independent variable, the coefficient of determination measures the goodness of fit of an estimated regression on the data. What is this coefficient of determination? That's just another name for R squared. Okay, but when we do multiple linear regression, what are we doing? We are adding more and more independent variables. The curriculum tells us that as we add independent variables, R squared just keeps going up. So if you want a higher R squared, you can just keep adding independent variables. R squared goes up even if the amount explained by the independent variables is not statistically significant. So if you think about this graph where you have K, and what does K mean? The number of independent variables. K is the number of independent variables. As K increases, we are saying that R squared will increase, but at a decreasing rate. And there is a cost associated with collecting data related to more and more independent variables. So even though in multiple linear regression you will often see the R squared number, what is actually more useful is something called the adjusted R squared. Okay, so R squared is less useful in multiple regression than it is in single variable regression. So instead we use something called the adjusted R squared. The adjusted R squared, denoted like this with this line bar above, is calculated from R squared using this formula. If you want to be super diligent, you memorize this formula. But I'll be honest, I have never memorized this formula and it hasn't hurt me. I've generally not seen the CFA Institute test people on their recollection of complicated formulas. But the concept that I'm talking about is important. What is adjusted R telling us? It is telling us that as you increase K, initially the adjusted R squared goes up, but then as you keep adding independent variables, the adjusted R squared comes down. Based on these pictures, you can say that at this point where you have the highest adjusted R squared, that's the appropriate number of independent variables to have. Now, what sort of a question can you get on the exam? 3 independent variables together explain 85% of the variation in Y. So you are being told that the R squared is 85%. Let's say that with 3 independent variables, the adjusted R squared is also 85%. Then you create a new model where you add several more independent variables. And would R squared go up? So R squared goes up, not by a whole lot, but it goes up. What happens to adjusted R squared? It actually came down. So is this model better because R squared is higher? No, it's actually worse because you need to be looking at the adjusted R squared. So the adjusted R squared actually was higher before, it's now come down. So is the new model better? It is not better because you have lost in terms of the adjusted R squared. Next section is using dummy variables in regressions. So what's a dummy variable? A dummy variable is a binary variable where it takes on a value of 1 if the condition is true and a value of 0 if the condition is not true. This is the first important point to note. The second important point is that if there are n states of the world or n possible scenarios, then you will have n minus 1 dummy variables. And I'll explain this through a couple of examples. If you recall level 1 equity, there was a segment where you studied various anomalies in the context of market efficiency. One anomaly was the January effect, where some data seems to indicate that returns in January are better than other months. So you decide in your market to evaluate whether the January effect holds. In your analysis then, there are two states of the world. Either it's January or it's not January. So what will you say? If you are dealing with January, then the variable is 1. If it is not January, then it's 0. There are two states of the world, and you just need one dummy variable, because one dummy variable will tell you whether it is the month of Jan or not. Right? So that is the basic idea. There will be several other studies that you do which rely on multiple dummy variables. For example, we look at example 5 in the curriculum now. What we are doing here, and I'm skipping the text, I'll just describe it to you. We are looking at the month of the year effects on small stock returns. We are evaluating whether the return on small stocks depends on the month. And if you get lucky here and you can show that in a given month the returns on small stocks are higher, then that can impact your trading behavior, right? So in your market, you try to run an analysis of whether the month has an impact on returns. There are 12 months in a year, so there are 12 states. If there are 12 possible states of the world, then how many dummy variables do we need? We need 12 minus 1, which is 11. So the way you can put it is, when B1 is 1, then it's January. Obviously, if B1 is 1, then all the other dummy variables will be 0. When B2 is 1, then it means it's Feb and all other variables are 0. How will you know that it's December? If all these B1, B2, etc. up to B11 are 0, then you automatically know that it's December, right? So that is how we are setting up this regression equation. So the returns for a given period T, and then expressed like this. So we run the regression, we feed a ton of data, we have 288 observations, run the regression, and then you get this ANOVA. So you need to do the analysis of variation. Now this is important. We talked about the F-stat before. Here the F-stat is 1.5. Looks small. And the significance is 0.12, which is 12%. Looks big. And that relationship will always hold. A low stat will mean high significance and vice versa. So can we reject the null hypothesis? With an F-test, what's the null hypothesis? The null hypothesis is that all the slope coefficients, and what are the slope coefficients in this context? The slope coefficients are the dummy variables. So the B1, B2, all the way to B11, these are your slope coefficients. They are also the dummy variables. So your null hypothesis is that all the slope coefficients are 0, and we run the regression. Can we reject this null hypothesis? How do we decide whether to reject a null hypothesis? You look at the stat, the F-stat, and then what do you do with the F-stat? You compare with the critical value. Okay, now at level 1, you studied the following. You studied that you use the F-stat when you have a ratio or you are comparing variances, but most people did not go any deeper. Here we'll actually look at the F table. So this is your F-stat. We are now going to look at the F table, and with the F table, remember we are taking a ratio, right? So we are taking this number, the top number, divided by this number to come up with the F stat. The degrees of freedom for the numerator equals 11, and the degrees of freedom for the denominator is 276. So if you look at the F table on the next page, and I'm going to go back to the P stat, this is what an F table looks like. So you are given that this is at a 0.05 significance level. You take this DF1 stands for the degrees of freedom with the numerator, that is 11. What was the degrees of freedom in the denominator? It's 276, so that you come down here. We are at 120 and then we are at infinity. So the number to pick is somewhere between 1.87 and 1.79. Okay, so let's pick a number somewhere in between. We would probably be, let's say we are closer to 120. So since we are at 276, let's pick 1.85 roughly. So what is 1.85? This is the critical value. Our F stat is only 1.5. It is less than the critical value. Since it is less than the critical value, can we reject the null? We cannot reject the null. So we cannot reject the null that all slope coefficients are 0, which means that we don't have any statistical basis for saying that the returns are particularly good or abnormal in any month. Does that surprise you? As general believers in efficient markets, that doesn't surprise us. And just to theoretically for a moment say that, let's say that you did find something like this, what will happen? Then you are not the only smart person, there are others who will also figure it out. Then everybody will buy in that month and very quickly the situation will go away. The other possibility is that there is a spurious relationship, but the learning objective here was that you are looking at this and then basically verifying that there is no relationship. Now once that's been established, does it make sense to look at all the t-stats and evaluate each coefficient? Then it doesn't. So that data is given, and even if you look at all the t-stats, they are generally fairly small. But once you have rejected at this level that the overall regression doesn't have much predictive power, what does the multiple R squared tell us? 0.05, very low. So from this, I'm sure if you calculate the adjusted R squared, that is also going to be very low. So this regression is telling us that we cannot reject the basic null hypothesis. Now, many people get confused with this p-value business. So I'm just going to show you that element also. The significance level is 0.1213, and I like what the curriculum says. That tells us that the p-value is this, shown for the f-test, so that's given here in table 4, this is actually table 4, means that the smallest level of significance at which we can reject the null hypothesis is roughly 0.12 or 12%. So if we have a 12% significance, then we can reject the null hypothesis. But we generally don't do things at the 12% significance. We do things at typically the 5% significance, maybe the 1% significance. So at a 5% significance, we cannot reject the null. Can we reject the null at a 10% significance? No. So can we reject at 12%? Then we are at the borderline. So only if we go up to 12.14% can we reject the null hypothesis. And this connects with the basic definition of the p-value. So p-value of this shown for the f-test means that the smallest level of significance at which we can reject the null hypothesis is roughly 12%. Okay, hopefully the definition of p-value is also coming through over here. We have gone over several terms, and I just want to summarize what we've talked about. This is not an explicit section in the curriculum, but I think it's useful. What is the f-stat? It's the mean regression sum of squares divided by the mean sum of squared errors. We've done this in the previous reading and this reading, so you need to remember this definition of the stat. The f-stat is used for the f-test, and what does the f-test do? It is used to test the null hypothesis that all slope coefficients are jointly equal to 0. When you are running a regression, this is the first big thing to do, the f-test. Then we talked about R squared. This is the explained variation divided by total variation. When you have multiple independent variables, this is also called the multiple R squared. In the previous reading, we refer to this as R squared, but when you have multiple independent variables, you might hear the term multiple R squared. And the reason I keep emphasizing terminology is because the curriculum keeps throwing these different terms at you, and half the questions can be solved if you know the correct terminology. Multiple coefficient of determination is another term used, and sometimes it's just called coefficient of determination. So the more questions you do, the better this will stick. And then we talked about adjusted R squared, which actually is a better measure when we use multiple linear regression. All right, so that is it for this segment. In the next segment, we'll get into the assumptions.